So we were talking about the SN1 mechanism, and one of the important parts of that SN1 mechanism is the carbocation intermediate. So let's talk a little bit more about the carbocation intermediate first. So we're going to have varying stabilities of these carbocation intermediates depending on what their structures are. So what is observed is that the most stable carbocations are highly substituted. So if we draw a highly substituted carbocation, I'm going to use methyl groups as my substituents. So we have a central carbocation here, and we have 3 carbon substituents around it. And so when we have a carbon with a formal positive charge, and it has 3 non-hydrogens around it, we call this a tertiary carbocation. And sometimes you'll see us abbreviate it as like a 3rd degree carbocation. Okay? And so as we replace, now we're going to replace our methyl groups with hydrogens. So we can replace 1 methyl group with a hydrogen, and we end up with a secondary carbocation. And sometimes it's abbreviated like that. And keep going. Now we replace 2 methyl groups with hydrogens. This is now a primary carbocation. And finally, the least substituted carbocation possible will be where we have all hydrogens around it. And so this is the methyl carbocation. And this is least stable. So our more stable carbocations are going to be lower in energy. Our less stable carbocations are going to be higher in energy. Okay? And so what is responsible for the increasing stability as we add more substituents is something called hyperconjugation. So remember that our carbocations are sp2 hybridized. So if we draw that out, and they are planar, right? We have an empty p orbital, right? And when we have substituents adjacent to our carbocation, say we have our methyl group, we're going to have adjacent sigma bonds. And so these adjacent sigma bonds are electron-rich. And so these electron-rich sigma bonds are going to sort of donate electron density back towards that carbocation. So the more substituents you have around an empty p orbital, the more stabilizing hyperconjugation effects you have. So when you go all the way down to methyl, you have none of these adjacent CH bonds that are able to donate electron density back into the carbocation, and that will ultimately lead to a less stable, higher energy compound. Okay? So we have a general scale from going from most stable to least stable now. There's another type of reaction. We've talked about nucleophilic attack, and we've talked about loss of a leaving group. We've talked about proton transfers. So one final fundamental reaction in organic chemistry is going to be a carbocation rearrangement. So in a carbocation rearrangement, we're going to go from a high energy carbocation, and we're going to rearrange it so that we form a more stable, lower energy carbocation. We're going to do this by rearranging the sigma bonds in a molecule. So I'll draw an example of this. And it will be a secondary carbocation. Okay? So it's already a fairly stable carbocation. Secondary and tertiary are fairly stable. Primary and methyl, these are very unstable carbocations, so you want to avoid drawing these in your mechanisms. But here we have a secondary carbocation, but if there's a possibility to rearrange it into a tertiary carbocation, that would be a beneficial thing to do. So here we have a tertiary hydrogen adjacent to our carbocation. So if we label this carbon 1 and this carbon 2, what we can do in our mechanism, we can take the electrons and the hydrogen. So hydrogen's moving here not as the hydrogen atom with an unpaired electron. It's not moving as H+. We're actually moving it as H-. And so H- we call hydride. So we're going to do a hydride shift where we take the electrons and we're going to move it from position 1 to position 2. So we're breaking the carbon 1 hydrogen bond and we're changing it into a carbon 2 hydrogen bond. So we end up with a structure where we have the new hydrogen, the hydrogen we moved, I drew that in at the secondary position. And now we have a carbocation at a tertiary position. So overall, we've decreased the energy of the system, so this is a very favorable thing to do. Right? So this reaction where we move a hydride atom, we would call a 1,2 hydride shift. So when you have a less substituted carbocation, if you can move a hydride just between two carbons that are adjacent to each other, that's a very favorable process, and we call that a 1,2 hydride shift. So we can do the same thing with other groups on molecules. So I'll draw another example. So again, we have a secondary carbocation where we only have 2 carbon substituents next to this carbocation. So this time, instead of moving, we have no hydrogen adjacent to it. So instead, we're going to take what is a methyl group, and we're going to do a methyl shift. So again, this is position 1, this is position 2. So we're going to take the methyl group with its electrons, so it's moving as a methyl anion, and it's moving from position 1 to position 2. And so we can draw the product of this, draw on the methyl that we moved, and now, where's our carbocation? Well, we broke this bond here, so we're leaving an empty orbital at this position. So now we have a carbocation at this position, which is a tertiary carbocation. Okay, what we're going to name this reaction, this is a 1,2 methyl shift. Okay, so sometimes you'll form a secondary carbocation, and you need to look sort of adjacent to it. Can we rearrange the molecule with either a hydride or a methyl shift to form a tertiary carbocation? That's something to look out for when working through problems. Okay? So which one of these is going to take priority? That's another question. So if you have the option to move a hydrogen or a methyl group, which one are you going to move? So generally, methyl shift or hydride shifts they're going to be faster than methyl shifts. You can think about it, hydride's a smaller atom, so it's a little bit easier to move a single atom with its electrons over rather than a whole methyl group and its atoms, so it's going to be much slower to move this than it is to move a hydride. Larger things can move, but that's much less common. So in the context of our class, we're primarily going to be focused on hydride shifts and methyl shifts.